No questions. I like it. So why I'm saying that is, if you did the homework, you're going to get a good grade. I will comment on it. If you have more questions afterwards, let me know. Okay? But we're all running out of time in this semester. This next homework, have you looked at it yet? Does it overwhelm you?
Doesn't seem like it should be too bad.
That's a problem with all Bayes homework. Make a point. They're all unidimensional models, first of all. The first one is to look at a article from JEM. Really, if you look at the model, the equation for it, equation 5, I think it is, there's like a phi function, and the numerator over a denominator, the numerator is 2PL, or 2-parameter numeral ogive. So that's your clue to go back to that code that we had as an example. And you're using fraction subtraction data in class, which I think we used in the example. So it's all tried to set up to be like grab stuff from example and put in. The second one is essentially greater response, but it's not, right? There's no parameters, but we're going to pump up the size of the we're going to turn a greater response, instead of multinomial, we're going to turn it as binomial. And so effectively the score on a greater response model that was 1 to 5, we're going to make it 0 to 4, and those are going to be successes out of 4 trials is the score, right? So it's a quick, easy trick to get a polytomous model that costs no extra parameters. So in theory, it should go all right. The problem is the polytomous model, as you know, make sure that you initialize all of the parameters. That's the one catch on that one. Otherwise, it'll be like, actually no, with binomial, I think it'll be fine. You can probably get away with it. Multinomial was the problem with that. The child doesn't match the parent. Fuck you, Jags.
Don't be so rude, R.
Seriously. Jags.
You don't know my life.
And I'm not even blaming this on R. R has its own problems. So anyway, today is a very special day, regardless, because today you get a crossover. This is like Infinity War, Chicago Fire.
Yeah, I told him about that yesterday.
Yeah, I think the big one was, what is it, Avengers last year? Was it the big crossover? Was that, I don't watch movies, so did someone watch that? Yeah, all right. Okay, anyway, Lisa effing Hoffman. That's her middle name, by the way. You didn't know that?
I like it.
Okay. Is going to give a couple lectures today.
Yeah.
Intermix with me. We're going to team teach. And we're going to talk about multi-level. Now why, before we get too far along, why is multi-level in a Bayesian psychometrics class?
Good question.
Anybody want to talk about that?
Well, why don't you tell him?
I'm not going to tell them. I want them to tell them.
All right, yeah. So I had him put up some lectures that I gave in my class this semester. We're not doing all of it, just enough to get to the point where you can follow along what he's trying to do.
And one thing I want to say also is this is just to sit back and relax.
Yeah.
Expand your horizons, make links between other classes type of deal, all right? There's no pressure here. None of this is going to be on the final exam. Wait, there is no final exam.
Yeah.
Just like absorb. If it's impossible, just take a nap. Or better yet, do this. Do this. Try to listen to it, and at some point, when it becomes less impossible, when it comes to you, you'll be like, oh, now I totally get it. That was the phenomenon I felt too. So a lot of this, when we get to the models that we're going to run, are really, really complex. Anyway, I'll stop.
Yes and no. I mean, it is and isn't.
Lisa
So,
effing Hoffman.
yeah, so this is the world of multi-level. You heard the expression that if you have a hammer, everything's a nail? Everything is a nail, because everything is a multi-level model. Every psychometric model is a multi-level model. Yes, sir?
Everything's a psychometric model.
Oh, there we go. It is.
What's the title of this class?
I will.
That was your class. That's like section 5 of ESQF 7370.
Yeah, no, but I'll prove it though. And so this is why when people talk about measurement and statistics, I always go, because measurement models are statistical models. They're done for different purposes, but they're all the same. So this is a different way of talking about it. What I want to convey to you today is how to do analyses on data that are dependent. So the idea of multiple people from the same group, multiple time points from the same person, that kind of thing, and how that intersects with the world of latent variable models, because they are all the same thing, just different terminology, different purposes. So when I teach this kind of stuff, for instance, this is in a longitudinal context, this is the very beginning of the story. So this is a classic, what's known as an empty means, where empty means no predictors. It's also called unconditional means, depending on your book which you're reading. But this is where everything starts. So in contrast to an empty model, like a general linear model at the top, right? If you know nothing else about a person, what's your best guess for their outcome?
A quick question for
Yeah.
you. What type of data do you have?
Right now, this is normally distributed residuals.
No, like from a person, what are you collecting from them?
Occasions.
Same variable, multiple
Over time.
occasions.
Mhm.
All right, so a person has 5 pieces of data they gave you over
Yeah.
time. Okay,
They're
that's right.
measured on one outcome 5 times, for instance.
Okay,
Something
cool.
like
So it
that.
could be like you give them some type of test, you add shit up, and you have 5 add shit up scores, right?
Yeah.
Okay, there we go.
Or they can be vertically equated.
Okay,
You've
there
got
we go.
5 thetas,
Equate
right?
shit.
Whatever,
Not the
right,
face,
it's
but
the
not
same.
bad. I shouldn't say that. No, it's good. Yeah, I gotcha. Just wanted to set up the data.
Yeah.
Okay.
Yeah, so longitudinal, but the same
That's-
principles work in clusters.
So please do continue with your question. I just wanted to set the data up. Yeah.
So if you don't know anything else about a person, what's your best guess for their outcome? The mean, right? So that's what this would mean. But in longitudinal data, we do know something else even if we don't have predictors. We know from which person each outcome came. So let's start with that as sort of our baseline piece of information. So the change in notation then, in all of my slides, I use red things for things that go into the model for the means or fixed effects, and blue things for terms that have to do with variance, model for the variance. So in multi-level notation, we split into 2 different sets of equations. Level 1, which is per time t per individual I, is given by this thing here, and note the big difference. Beta takes up an I. It's an individual intercept, but this beta itself is not a thing. It is a placeholder for a linear combination of things to be defined at level 2. And so even is per occasion per person. So we come over here to level 2. How does each person get their own intercept, their own mean? Well, same principle. It starts off with the grand mean for everybody, which is gamma, this wide-looking thing here, plus u, which is a random intercept. How far off your mean is from the grand mean. So when you put it back together again, it looks like this. The composite equation, and this is the version that Jonathan uses in his code in Bayes.
But I do have
Right.
multi-level written in LaTeX.
Did you?
So.
Okay, so, the idea that this is my new sort of best guess for somebody, their own mean, which is part what everybody gets fixed, and then part what they get random. And in terms of like the total variation, we haven't explained anything. It's not appropriate to think of this as some sort of predictive model. All we've done is take the total variation and split it into 2 kinds. That is due to between person mean differences, and that is due to within person variation around those means. They're both technically error terms in that we don't know why some people have a higher mean than others. We have to get predictors in a model to find that out. Likewise, we don't know why some occasions are higher than others, so they're both errors of 2 different kinds within level 2, level 1.
And can I add one other thing, because we're supposed to team teach.
Yep.
If you're, Ben, you talked about reading Gelman's book, it's kind of a orangish and black book about hierarchical models. A lot of times the Bayesians will take the terms in the parentheses and combine those into just a beta per person.
Mhm.
And that's the one big divide between what Lisa's talking about, which is a not necessarily Bayesian, but not excluding Bayesian way of framework. Kind of the HLM framework that grew from Brick and Bradenbush, or even before that probably, the one that made famous by.
Mhm.
So I make that that discussion because our base code here, when we get to it, is going to be more toward this version. Whereas if you look at other people in the world doing Bayesian and multi-level, they will combine the random effects with the fixed effects to give you everybody a beta, putting it back together.
Okay, so we're skipping ahead. So in terms of longitudinal then, introducing the effects of time, we have 2 things we want to know. On average, is there change? So if so, there's a fixed effect, where in this case, fixed means the part that everybody gets added to their score. Then also the part that is unique to these models that ANOVA can't give you, for example, the idea of a random effect of time. Does each person need their own slope? And you can have either, neither, or both of these things be true. Here's some pictures where I try to illustrate this. The intercept is random in every figure. The x-axis is supposed to be time. The solid black line is the mean for the sample. and then the individual lines would be trajectories for different people. So if we start with the top left here, this is a picture that has neither a fixed effect of time nor a random effect. There's no fixed effect because on average there's no change, and there's also no random effect of time because no change is the same. Over here, there's a fixed effect. There is change on average, but everybody changes the same way, so we don't need random. The bottom two pictures then are instances in which we do have a random effect. Everybody needs their own slope, and that can be true whether or not there's a slope on average or no slope on average. So fixed versus random. The bottom two pictures, another way to think about this is that we're now saying that people differ from each other in two ways. There's two sources of dependency that's introduced because of longitudinal data. One in mean level and one with respect to time. So if we expand the model then to put a fixed effect of time, in multi-level notation we pick up another beta placeholder. This is how each person gets their own time slope. We come down here to level 2, for now it's just fixed. So this model says everybody changes the same. So if we put it down into the composite, that's what it looks like. Skipping ahead, matrices. Here's what it would look like if we add a random effect, where here's the U1 term that gets picked up. So now that things are in parallel, where the fixed effects, the gammas, is what happens on average. So the intercept would be the expected outcome when time is 0 on average. This fixed slope is the expected rate of change per unit time on average, and then the U's convey how far off yours is. So then when you put it back together, you get this sort of combined equation down here, where now there's 3 kinds of variability in the model that describe this outcome. There's mean differences between people captured by the intercept, specifically at time 0 in this case. Slope differences between people, so those are both level 2 between person sources of variation. And then there's E, which is level 1, which is like, why are you off your line today? What is it about today that makes you off of your trajectory? And if you think about what could logically explain these sources of variance, only people level predictors. Why do some people start out higher than others? Something about you that's constant. Why do you change more than other people? Something about you. Why are you off your line today? Has to be something that happened today. It can't be something that's constant, like your education level. I have a PhD every day. That can't explain why I'm better today than yesterday, or vice versa. So the whole logic of multi-level is that you're taking all of these sources of dependency, you're capturing them in a variance component, and then you're finding predictors that then explain that variance component. And on the statistical side, the partitioning of variance in this way makes sure that the standard errors that go into testing those predictors are as accurate as possible, because they're only based on the variances that are relevant in terms of that effect. Okay, so in this model then, one might be tempted to stick in another time-varying predictor, something that was measured at every occasion. So for instance, if my outcome is some sort of measure of physical health, I might want to correlate that with perceived stress each occasion, thinking that feeling stressed out is bad for you. Sure, so I can stick that in here as beta 2, bring another equation down here, put in a fixed effect, maybe a random effect, and you will see people do this in the world. Only one problem. Can someone tell me? Ninja, why is that a problem? You forgot? Why is that a problem?
Level 1 things can carry level 2 information.
They're smushed, exactly.
I always like to think about it, anything that happens at level 1 may have an analog at the higher levels above in your study.
So
It's a hard thing to remember, but it's true.
So think about time. If I have a study in which everybody is measured at the same occasions or nearly so, right? There's no between person variation in time. So I can put the effective time in level 1, knowing that it only carries within person variation. Therefore, the only kind of effect it can have is within persons. It only pertains to one level. Likewise, I could put in a level 2 variable like gender or group or something like that, and know that it only contains level 2 variation, and therefore the only kind of effect it can have is level 2 between. If I put in something like stress here, and I ask you every time I measure your health, how stressed you feel, some people are going to report more stress on average than other people. that's not time varying. That's time constant, that's level 2. So when you put a predictor in here that varies both between persons and within persons, and you give it only one effect in the model, you have to assume without testing that that between person effect is the same as the within person effect. It's an omitted variable problem, essentially. And in longitudinal data, that will never be the case. Not just because stress means something different at each level. Like the reasons why some people have more chronic stress in their life are different than the reasons why some days are harder than others. So conceptually, it's a different variable, even though you're thinking of it as the same thing. But also numerically, these are all unstandardized coefficients on different scales. So only if X and Y are on the same scale and each has the same relative proportion of between and within variance, that's the only situation in which you have a chance to have the same effect between as within. So it's not gonna happen. So the correct way then to deal with the problem is to try and find a way to represent stress at level 1 and at level 2. Do you want me to talk about person-centered? Yeah, okay. So switching gears.
Sorry, I'm not trying to, I'm not sure overload on this. We're trying to find a way to mesh like content from 2 classes, because there is a part where they're the same.
I need lecture
where
9.
Where you relate this to the latent variables by any chance?
Oh yeah, you want me to do that first?
Yes, please.
Okay, yeah, sorry.
No problem. If you scroll, here, let me, do you want help with math? 2 fingers as you're scrolling.
Okay, I'm getting down to this. And okay, yeah, back to our regularly scheduled psychometric course. There. How do I make this big?
The green thing on the top left.
Okay. There. Okay. So that's all fine and good. And those are mixed models or multi-level models. But guess what? That's a latent variable model because everything is a nail. So it's not a coincidence that when I make pictures of these sorts of models, and the website for the longitudinal textbook I wrote is called Piles of Variance. That's what I call them. I make circles. It's not a coincidence because what we're actually talking about is latent variables. Random effects, those individual intercept and slope deviations that I had denoted as U's, those are factor scores. They are latent variables. So once you understand that a latent variable is a random effect, you can start to see how these same models can be expressed as factor models. And this is not new. This goes back to, God, what, the 80s, 90s probably? The earliest article I know of is Meredith like 92-ish. And there's been a whole lot of tutorials mapping mixed models onto latent trait models. So I'll do that for you here. So in my notation, for instance, this is a CFA model because we're talking normal residuals. All of what I have to say translates into I or T2. You just have a different link function for the individual responses. So each occasion would have an intercept, a factor loading times a factor plus error. That's what it looks like in the CFA world. My version is down here, where I have 2 latent factors, and the U's become the F's. The only catch is that rather than estimating a factor loading, I am going to fix it to be a function of time. And how I fix it denotes what type of trajectory I'm trying to estimate. So it looks like this. So in the world of CFA, things in boxes are real, observed variables. Things in circles are pretend. Excuse me, latent.
Circle plus square is not equal triangle.
Yeah, there's no
But this is
triangles
good.
in this. I hate the triangle. I'm not doing the
The
triangle.
eye of providence.
So a general linear model, a regression model, would look like this in this type of notation. So here's the model, here's the diagram. So we create a latent variable that has only a mean. That's gamma 0, 0.
That would be in the triangle.
I know, and I hate it. I'm not doing
I hate
the
it. I
triangle.
hate it too. I'm just joking. I had to do that because I know.
Yeah. But the
Wait,
variance
is this an
fixed to
EFA?
0.
Is this an EFA?
I don't know why about. The factor loadings here are fixed to 1. So this is a fancy way of saying I'm estimating the mean across occasions. There's 4 occasions here, 4 boxes. For symmetry with the mixed model version that I showed you, I'm fixing all of the error variances to be equal to each other. And the default when you fit these models as structural equation models is not that, but it actually becomes problematic. I'll talk about that in just a second. So this is the analog. If I want to get to a longitudinal model where I have two kinds of variance between and within, that is achieved by giving this intercept a variance. So in other words, the mean of this latent variable is the fixed intercept. Its latent variance is well to random intercept variance. The level 1 variance of E are the residual variances down here. And in the standardized solution, the standardized loadings would give you your interclass correlation.
What?
I know.
Interclass correlation hasn't been defined.
Yeah, I know. We don't
It's
need to
okay.
know that.
There's more terms in multi-level to describe things, and kind of the big, can I just jump in real quick with the big difference? The big difference, I think, in concept, I always liken it to data. If this were a factor analysis, those Y's would be item responses.
Yeah.
And there's nothing to keep us from having those being item responses, but if you think about the type of data, the design for data is item responses are multiple pieces of observation coming from people, just all pretty much at the same time. We don't lump those across time. I think that's the big conceptual difference. After that, you've got a model where you're fixing parameters and it'll give you the same results, more or less. I mean, there's some issues with estimators and so forth, but
It will be, if you use the same estimation and you fit the same model, it will be identical.
Mhm.
The only catch, these variables typically have intercepts. If they're items that get estimated, we've shut them off. We've shut them off to force this to become an intercept. Otherwise, it's not identified. So we're saying right now, all of these intercepts are the same because they are all the fixed mean of this factor. That's what their intercepts are. That's not right, but that's the jumping off point.
when this next slide comes up, can I just jump in? That one, when I first saw that was my first job at KU, I'm like, really? People do it that way? Why? But then I get to, okay, yes, there's a big.
Well, I'm following the convention that sometimes where the variance of something that's the residual leftover is in a separate circle.
Oh, I didn't even mean the zero variance. I was
Okay.
talking about the two circles to describe a growth model. Anyway, go ahead.
Sometimes you'll see like a two-headed arrow attached to this that denotes that it has a variance. This is the way that.
And I'm not,
I've seen it.
for the record, I'm not picking on Lisa or any of this. It was just when I'm used to seeing the mixed model notation, which is not anything to do with this. So when I first saw it put as a factor model, I was like, why are people doing it that way? But then I was like, oh wait, let me think about the combination. And so that's where I was coming into that world from. That's all I wanted to say.
So we don't have a variance yet, but we do have a mean, and the mean is the fixed effective time here. And I know that this is linear slope because I defined it as such. So these are fixed. You have to make one of your occasions times 0 for the model to make sense. It doesn't matter which one. Other types of forms you could have. So for instance, if you wanted something nonlinear, like a log slope to make an exponential, if you tie these to be log values of time, for instance. Another thing that's popular in here is what's known as a latent basis model. That's harder to do in a mixed modeling software. What you would do in that case is fix 2 of the loadings, usually the beginning and the end, and then you actually estimate the others. And so it becomes some kind of nonlinear data-driven trajectory for like how much change has passed. This assumes that equal change has happened at each occasion, but that's a testable hypothesis. So all of the same functions that you would describe nonlinear change as are available to you in this framework. And then if you pick up the variance here, then you're at the same place we left off, which I would call a random linear time model, where you have 2 sources of between-person variance, 1 source of within-person variance, and if you want to map it onto the mixed model equations, it looks like that.
Whoa. Can I ask a question?
Therefore, everything is a nail.
Is this a latent growth model?
Yes.
Sorry. This is the funny thing with it, because if you come about it from the mixed model world, you're like, there's nothing latent, right? I got random effects. I guess I don't observe those. Whatever.
They say that's why it's latent.
Yeah. And then you're like, well, no, I'm gonna do a multi-level model. I'm gonna do a growth model. Well, I'm gonna do a latent growth model. Like, what's the difference between the two?
Whether you fit it with SEM software or mixed modeling software,
And you know what? Guess what? JAGs don't care.
JAGs don't care.
Bayesian software you can set up however you want. With the general software you can set it up mostly however you want. There may be some catches in certain areas where it may be different, but It's just, I'm making this point because what we would call, if we're coming about this whole class being Bayesian psychometric models, we would call this the latent growth model. But it's also just a random linear mixed model, right? So it's the same terminology, different same stuff, different language. That's all I wanted to
And
kind of
often
cross
you
over.
have to throw the word curve in there. It's a growth curve model.
But there's nothing curving here, though.
Doesn't matter.
That's why I carefully chose my words to not
No,
say
but
curve.
I'm saying these are called growth curve models, even if you are declining in a linear fashion. It is a growth curve model.
Yeah, the linear slope don't curve, right? Now, if we throw a mixture on top of it.
No. Here, let me explain why that's stupid right now. So I've seen this, and I've had to sit through workshops where people did this, and I'm like, face palm. So what happens is that people put a mixture on top of these intercepts, excuse
So
me,
that each class has a growth curve model.
a linear growth curve model. How many kinds of linear are there? Right. They think what they're doing is allowing different types of trajectories, but if you put your mixture on the definition of a trajectory, all you can have are different classes of linear, which is what you already have with these things as continuous variables. So we end up with latent mixtures where it's like, this group has an intercept here, and this group has an intercept here. Like, how does that help me? So, no, the idea is that they want different patterns of change, but putting a mixture on top of a linear slope will never get you that. So.
I'm just throwing in everything that I just hated on this year. It's a summary, but.
Well, so if we have nonlinear change, let's say that there's some sort of quadratic change, can you guess how we would modify this? Add another set of circles and make the loadings times squared. Likewise, if you wanted to make this a piecewise model, where you had a different trajectory between 0 and 1, and then a separate trajectory between the others, you change the loadings to convey that idea, and you have two circles. So, yeah. Alright, so that, you want that?
But we're good. Are we cool? That's the crossover, right? And now we're gonna go back to regular scheduled multi-level, but just remember, whenever she says random, think factor, because we're psychometric.
Where's your
Right?
escape key?
Does anyone have any questions? While she's looking at slides.
I need to get lecture 9 out. How do I do that?
Let me help you.
Yeah. See, I can do all this. I can't work a Mac, as it turns out. They make me feel like my mom. How do I get lecture 9
This is
out?
how I feel with Windows now.
Do I need to update my computer when it asks me?
And
Yes, you all have parents who play tech support for, right? You know these questions. It's giving me this error message.
My dad doesn't have a computer or a smartphone, so my life is easy.
I'm gonna put your sidebar over here. If you want to move it 2 fingers. All right.
And I'm gonna have a sausage roll. Anybody?
Okay.
I can play waiter.
Let's see. So do you want me to do person mean centering and stuff, or you want me to go straight to multivariate?
Personally, it'd be great to set that up if you're willing.
Yeah, sure.
I mean, you're working here. I'm not. I'm like, she's teaching for me, and I'm like sitting here eating snacks.
So before we took the sidebar into latent variable land, we were talking about the problems of level 1 predictors. So in the example that I had time being balanced, and therefore it could only have a level 1 within person effect. I don't have to worry about it. So the problem comes in when you have time varying predictors that have variance at level 2 and level 1. You've got to represent both of those things. And so there are 3 potential effects that you would be interested in predictors in which the only source of between person variation is in the mean. So this would happen when you have outcomes that are supposed to fluctuate over time, like if you have a daily diary study or something where you beep your phone and you answer a couple questions about how you're feeling. There's a lot of studies that look at the interplay between, say, stress and emotion and physical well-being and social support and all those kinds of things. Those are longitudinal studies, but they're not about change. They're about people's sort of normal fluctuations and how different events perturb those fluctuations. So this is the type of model that would be used to address that data. So like if I think of stress as my time-varying predictor, to the extent that some people are more stressed out than other people, that's a level 2 between person effect. It should capture level 2 random intercept variance in my outcome. To the extent that some days are worse than others, and that matters, that should capture level 1 time-specific variance in the outcome, and I've grayed out the last one because I don't want to talk about that yet. So there are two main ways that people talk about putting this level 1 predictor in the model. Level 2 we'll set aside for right now because I want to show you what not to do. This is the wrong way. Cue the, what's that group?
We don't need to
No,
talk about
okay,
it,
never mind.
yeah.
There's a song that's terrible and that's the name of the song, but this is the wrong way. So this is what people would do. Let's say that this is an outcome where we don't have systematic change over time, it's just fluctuation, so they throw in their time varying predictor. Seems reasonable. Let's say they've even centered it so that 0 means something. The problem is that if this say we're stressed, this is both some people are more stressed out than others and some days are worse than others. And you're only giving those two things one effect to share. So this is the problem that I refer to as this is a smushed effect because the level 2 and level 1 effects are like smushed together.
I think it would be possibly smushed.
It's almost
It's a
always.
strong assumption, yes.
A nicer way to say that that's more formal, a conflated effect is probably my second favorite, convergence composite. But this is a well-known problem in multi-level in the sense of conflating level 2 between person mean differences with level 1 within person variation, so.
And by the way, it's amazing how many people who do multi-level never consider this.
The number one thing that people screw up with a bullet. So I have a picture that describes that. Here's how we fix it. In longitudinal data, the easiest way to fix it is to make the two variables directly yourself that represent the variability at each level. So at level 2, we would take the person's mean across occasions, center it such that there was meaningful. For instance, if we picked the grand mean of this variable as our centering constant, higher values on this new person mean x would mean I have more of it than other people. At level 1, we take that person mean and we use it as the centering point. So the big difference here, this is a variable, not a constant. By subtracting off the person's mean, we have rendered this new predictor orthogonal with the other one. So within person x is purely level 1. A 0 value means that I'm at my average, whatever that is. A high value means I'm more than I usually am. What I usually am is up here. So I've taken my predictor, I've split it into two observed variables that each convey their own effect, and then I stick it in the model like that.
If you put a mean in, and say you have a 5 time point study, is the mean, when you have a linear model, you're putting in an X predictor, you're assuming perfect reliability. Is that assumption met by putting a mean in for this type of study? Just something to think about.
That's my next picture.
Oh my goodness,
I
it's like
know,
I know
right?
you.
I know. So now you can't screw this up. This is why I teach people to do it this way. Because the new predictor has only one level 1 variation, its effect has to be within person effect, has to be. The new level 2 predictor has only level 2 variation, its new effect has to be the between person effect. Can't screw it up. Conceptually, what we've done is create a system for our predictor that mimics what's happening on the outcome side. So on the outcome side, we let the model partition the variance into level 2 between person intercept and level 1 within person residual. We have tried to do the same thing with observed predictors, where the person mean is the brute force way of giving ourselves a random intercept, and the within person deviation from that mean is a brute force way of getting residual. But then you look at this and it's like, well, wait a minute. Why are these observed variables on this side, but those are latent? Why are these not being treated the same way? If you want to treat them the same way, then we replace these boxes with circles, skipping contextual effects right now, like that. So,
And this is now
so
multi-level.
yeah. Oh, now this is a multi-level structural equation model.
Oh, the tie to psychometrics again. What?
And you know why? Because these circles are latent variables. And so let's back up here. This is just a mixed model. This is a multi-level structural equation model. Doesn't that sound so much cooler? I have a problem with that notation, that verbiage, because do you see like a measurement model here? Like, do you see items measuring a factor? No. They call it that because a random intercept is a latent variable, by the same logic, a residual is a latent variable, and so they say this is multi-level structural equation model. I call that this is a multivariate multi-level model. There's two outcomes being partitioned at the same time.
And back to my comment, the mean itself, you think about it, you have a 5 occasion mean, it's gonna have a standard error of the mean. You put that into the not multivariate version of this, the
That
previous
one.
version. So now all of a sudden that predictor that's at level 2, that X bar, it's got error to it. It's not reliable, it's not perfect. So it's sort of violating assumption. You can imagine what that does to the fixed effect for that as well, right? You're gonna have a smaller amount of standard error because you think you're more certain about where that mean happens to be per person. So there is some motivation to treat that more as that itself being an unobserved quantity that we're trying to measure imprecisely, because that will hopefully help with standard error estimates, but also may help in other ways as well.
So the difference between this model here with the boxes for X versus the latent variables, the logic is the same as switching from a path model to a structural equation model. These things are supposed to be corrected for error, right? So the relationship between them should be better than if you assume that this is perfectly reliable. There's been a lot of research on this that suggests, yeah, that's the case, with a caveat though. In situations in which you don't have a lot of information with which to estimate these intercept variances. So when you don't have a lot of people, or the amount of variation at this level relative to here is small, this is a lot noisier up here. It's a lot less consistent, as you might imagine. It's just a more complicated model. The other thing that differs is in terms of software. When you treat it as a box, you can use univariate multi-level software where you have REML as an option for estimation.
Like Elmer
Which
and R,
it,
LMA4.
It gives you more accurate random effect variances in small samples, as well as denominator degrees of freedom methods that do the same thing. The only way that I know how to estimate this model is using regular flavor maximum likelihood with no denominator degrees of freedom, which is a nightmare for small samples. So there are reasons for and against if you're in the world of maximum likelihood instead of Bayes. Likewise, let's say that I wanted to ask if this relationship here differed as a function of some other variable, right? A moderator. I could do that. I put in an interaction term between my moderator box and this box and I'm good to go. If I fit the model this way, now all of a sudden my moderator is another latent variable interaction. And that requires numeric integration if you do it with maximum likelihood. I've only fit one of those per model without it throwing up at me. So it gets a lot more complicated when everything is a circle to try and figure out what else you can do. So where this falls apart, where you don't get a chance to choose between this and have a reasoned argument on either side, is when your time varying predictor itself shows individual differences in change. So I have these two pictures here to illustrate briefly. If everybody changes the same in your time varying predictor, so either there's no change or everybody changes the same, there is only one source of between person variation, and that's in the mean. And so making a box is maybe a reasonable thing to do. But if you had data like this, you'd have to make a second box for between person slopes. And that is a terrible idea. That's what people did in the 80s before multi-level came out. It's called slopes as outcomes. You don't estimate a slope and go stick it in another model. That's bad.
What could go wrong?
Well, is the slope reliable?
Oh, it's whenever you take, I think one of the fundamental problems in all of psychometrics is the same as fundamental problems in all of statistics. It's when you take something that has error to it and treat it as you don't, right? When you put a mean in that has a standard error of the mean, particularly when you have like 5 or 7 observations, bad things happen. When you take a slope that has a standard error of the slope, particularly when you have bad things happen. Alternatively, if you are taking a theta from an IRT model and you don't have 180 items, where's the variance go if you go do something with just the point estimate of the theta? Bad things happen, right? Potentially could happen.
So think of this as having like 4 items, right? That's what we're doing here. So, and think if you have 5 items for everybody and one person only has 3, do you trust their mean and their slope as much as somebody with complete data? No, but there's no way to do that if everything's a box. You can't differentiate which boxes are better or not. So that's the point at which you really do need multivariate, multi-level, is to be able to partition the variance that's between persons, intercepts, and slopes in the predictor along with that of the outcome.
You know, I use the multi-level SEM for that.
Sure you do.
It was exploratory. With an exploratory mixture multi-level.
Oh, I just threw up in my mouth. Okay.
I'm just trying to see like how many times we can make each other angry, like, frustrated. I'm just trying to have fun with this. We're trying to be relaxed. This is like information overload. You could teach an entire course on this, and guess what?
I do.
Yeah. So, right?
Well, this is usually like the last month of the advanced course I spend on all of this.
But your clustered course, you're going to get more into the time one predictors, right? So and I think that's one thing I wanted to know, the big difference between the time and the clustered. The methodology is the same, but you think of time as a huge design event.
Time takes like a whole semester just to get through.
It's like your study design, you have it across time. That's a huge thing that you have to worry about methodologically and statistically. Whereas in the clustered case, time isn't there, but so that means you can go quicker into more of the like level one predictor idea, perhaps. Right? Did I summarize that correctly?
Yeah.
So anyway, just saying that I know it's information overload. Sorry, just we're hoping that it expands the horizons a little bit, but it blows my mind sometimes. It takes me forever to get back into it because my mind is more on the psychometric model. Even though they're the same, it takes me a while to get back into the terminology and whatnot. So anyway, thank you.
Yeah. So, I mean, beyond just the statistical side of making sure all the dependencies captured so that you can trust your answers, it causes you, I think, to think differently about how you phrase your questions. So, does X predict Y? That is not an adequately phrased question, right? X predicts Y in 3 distinct ways in this slide alone, and there's probably more. Do people who start out higher in X start out higher in Y? Do people who change more in X than other people change more? And at occasions where you are off your trajectory, say you're higher than predicted, are you also higher than predicted in Y? And that's 3 ways. And so when you're thinking about hypothesis testing, like keeping track of all of these different ways things can relate to each other becomes important. Let me just show a couple pictures. And we're skipping all this. Sorry, you don't get to come to my class. This is this. I just want to do this one.
It needs to die. I don't see EFA on that slide.
Well, you already tried to kill this off. So,
Okay, yeah.
this is a common way of doing longitudinal data for people who've never taken a longitudinal class. They just throw it in a path model and do this. Now, what could possibly go wrong? They're interested in whether X comes first, predicts the next Y, or vice versa. The logic behind this is to try and see which came first, right? The chicken or the egg kind of thing. But what's the problem here? Smushed. These paths in the middle are not intercept relations, they're not slope relations, and they're not residual relations. They are a smushed amalgam of all 3 things at the same time. So if you wanted to test these sorts of hypotheses, you have to be able to keep the between-person variances in the story. And this picture is stupid right now for the same reason.
But if I put it in a multi-level SEM, will it work?
Only if you do it properly. So these are longitudinal mediation models where these paths are smushed too. So don't do that. Do what he's going to show you instead.
Well, I based mine off of your example, so. Well, Lisa's gonna show you, but I translated it into
Yeah,
Japs.
this is, we did that. Here's some pictures. Yeah, I don't think we want to do any of that.
Does this look complicated?
Yeah, no, then this is like how you would do that in a proper way. You get the same sort of cross-like paths, but you also have your intercepts and slopes.
By the way, how many variables do you have in this model?
2.
Like, that's 2 variables across time
Right?
points.
I got
That's the thing that
Y and a
multi-level
Z.
does, right? That's the hard part. You think about it, you go step back, it's like I collected 2 things at 5 time points from people. That's a fairly simple research design. So the layers of complexity that go into it when you start thinking about the different types of variables, it just give you some pause. Now that doesn't make you want to be overwhelmed, but just think about that when you start getting into your research is what possibly could be layered on top of this. So,
Do you want me to do contextual things?
yeah, why not?
Okay.
Do you want to?
Sure.
Well, I don't want to,
I gotta
make
go
you do
back.
something you don't want to do.
Um,
I'm grateful for Lisa's presence every day, but especially today.
nice. That's nice. Okay, so this is like when I teach multi-level and I don't have time to do any of the multivariate, I'm like, do it this way, because this, you can't screw this up. But this is not nearly as common in cluster data. Another way of specifying the model is more common in cluster data, and unfortunately, that way is the default when you estimate these multivariate longitudinal models in ML, as well as in at least what you started with in Bayes, you phrased it that way, and then you managed to fix it, right?
Mhm.
So, let me back up here. Let's see. So this model, right? This model that's way wrong, how people will fix it is to add in the person's mean. So, the third question that I skipped over that you might want to know is another type of level 2 effect known as a contextual effect. You can think of this two different ways. I think of it most easily as a test of whether or not the level 2 between and the level 1 within effects are the same. The contextual effect is the difference. So it is the empirical way to test the appropriateness of smushing.
Where's the word contextual come from?
That's what I was just going to
Sorry to interrupt you.
Yeah, so it comes from its use in cluster data, where the contextual effect is the incremental effect between groups above and beyond the effect within groups of the individual.
What?
Exactly.
The context of the group
Yep.
causes
So-
certain things to.
Here, I'll do it here. SES predicts achievement, let's say GPA at the individual student level, right? We'll say that that's the case. But are children randomly assigned to schools in this country or any country? No, right? Kids that are well off live in neighborhoods where there's lots of nice houses and they all go to a school that has more resources. So how do you tease apart the idea that you are from a affluent family versus you go to a school with lots of resources? Two different things. So you can put in the model individual students' achievement predicts individual GPA, as well as the mean SES for the school is a level 2 predictor of school differences in GPA. And if you put in the original version of SES, or you center it at a constant, then this becomes the within school effect because you've controlled for this one. This one, though, is the extra effect of going to a rich school after controlling for how rich the kid is. That idea of extra effect of the context. It's what does the group have to offer above and beyond. In other words, if I was a poor kid, this is the benefit that I still get because I go to a rich school.
You can even like the student level, they might have access to tutors and stuff. At the school level, they've got a really nice computer lab and what have you.
Mm-hmm.
And all the friends are have parents that are fairly stable and not transient, and
Yeah, there's
all sorts of benefit that doesn't.
Yeah, I'm not going to
captured by
pretend to be an
SES,
educational
yeah.
psychologist in this crowd, but yeah, I mean these are different things, right? Is the idea. So phrasing the model to get the extra effect is known as the contextual effect, and in the context of longitudinal, this makes people's head hurt because level 1 here is child and level 2 is school. In longitudinal, level 1 is occasion. An occasion is like not a thing, the way that a child is a unique entity. And so thinking about controlling for the occasion makes people's heads hurt.
It kind of brings back a philosophical point. Are you the same person you were two hours ago? Right? You can think about that. Time within person is completely the same.
So this is the version of the model that when you fit a longitudinal multivariate model, this is the version that you get for some of the parameters, at least in M+.
I'm getting cues that I need to be more quiet.
No, I'm just saying. I'm trying to get to the point where
I know.
we
It's
can
okay.
kind of
We're coming up on a break in a little bit. We'll get there. It'll
Yeah.
be okay.
So I have time varying X here. This is the uncentered version, or it's centered at a constant, doesn't matter. Point being, this is the original time varying predictor. It still has both level 2 between and level 1 within. However, I'm controlling for person mean, the level 2. So if you think back to the idea of unique effects in regression, right? If you put two predictors in the model at the same time, each one is controlling for the other, so its effect is going to be different than if they were by themselves. So think about what is unique about each of these predictors. Time varying X has level 2 and level 1. Person mean has level 2. So what's unique here? Level 1. So it ends up that even though this is a different variable than is used in person mean centering, its effect is the same. because of statistical partialing in the model after
Controlling
controlling
for
for person mean X. But this thing right here, this is not the effect of the person. This is the effect of the person after controlling for the value at that occasion. And in longitudinal, you're like, meh? And that's hard to understand. But the good news is that these are linear combinations of each other. Between minus within is contextual, within plus contextual is between. So if you don't like whichever version of the level 2 effect you get, you can switch to get to the other one by asking for it as a linear combination, a new parameter in M+, an estimate statement in SAS, and so forth. But knowing which kind of level 2 effect you've got is critical, and making sure that every level of the model at which a predictor has variance gets an effect. That's the thing. No smushing and know which kind of level 2 you have. Then you're good to go. There.
Thank you.
That's it.
So, I have a question. So, for this model, we still can add a interaction effect between level 1 and level 2 to control
The slope?
the slope.
Sure. But you, you could, but that interaction would be smushed.
Okay.
So you would have to add an interaction with the between part also, or a quadratic effect, in order for it to become unsmushed.
It really becomes crazy. You put a squared person
You have
mean.
to put a square term in.
It's cool. It's like really cool. Once you think the stat part of it is really cool, for me to get into it, I have to go so far. I have to like immerse myself in thinking of this language to get there. But it's really cool. You can do that. But it's not fully there.
What basically the general rule is that whatever term you put in for this predictor, you have to put in its analog with person mean X for it to be unsmushed. So if you put it in as a main effect, this goes in as a main effect. If you put this in as an interaction with anything, that goes in with an interaction with anything. Otherwise, you are assuming the within and between effects are the same of whatever you just added. Whereas in person mean centering, that's not the case. If you leave out one of these, you're assuming it's 0, the same as when you leave out anything. So that's why I prefer this method, because it's harder to screw up.
One other thing I wanted to also note is that what we're going to see in the example, with JAGs, we have complete control of what we put in our model lines. But that's not always the case in other software. And behind the scenes, what matters is what it's putting in each of these spots. If you think it's one of these, and it turns out it's not, it's the other one, the effect and the interpretation of the effect changes, which is a paper that you've got coming out. I'm not trying to steal your thunder,
No,
I'm trying to set it up.
No, you can steal it, because it's already accepted.
Yeah, so I want you to, I'm trying to leave it. That's sort of the context of this example we're going to get to, but I want to set you up to talk about that. That's where I'm trying to go.
You want me to talk about that?
Yeah, why not? Why don't we talk about that right now? Yeah.
Okay, sure. So M+ is the software that I use to estimate these sorts of models. And they have a maximum likelihood version, and they've been increasing what they can do in Bayes. And this contextual versus level 2 thing came up recently because they added something for Bayes such that they do latent centering. So they make it so that it's basically this version using latent variables, so that the level 2 effects are all between rather than contextual. And that's fine, except that then they published a paper where they ran ML against Bayes. When the ML version of the model, because of the way that they left it alone and haven't updated anything, the ML version of the model is that one. The Bayes version of the model was this one.
How much does the syntax differ?
None.
That's the problem.
The exact same syntax triggers something different under the hood in terms of the model when you switch estimators. So ML is the other one, the contextual version, Bayes is this one. So then they published this paper running a simulation in Bayes, and then they did the same model in ML, the same model, it wasn't the same model, in ML, and said, look, ML stuff is biased, Bayes is better. I'm like, no, it's not the same model. So I had to write a paper because it made me so angry. And it's coming out in the new APS journal, Advances in Methods in Practice. So there's a special issue on multi-level coming out at some point. I'm happy to send it to any of you if you care. But yeah, what it turns out is that because these are linear combinations of each other, you can prove, and I will say prove, like that it's the difference between ML and Bayes is the model. Because the simulation had giant samples and they didn't put any kind of informative priors.
So this is kind of like last week when we did this, the forensics with JAGs to see what was happening with the missing data.
Mhm.
The forensics you were doing with ML versus Bayes and reading this, you're like, I think this is contextual. I remember you talking about it, right? And so, anyway.
And they put, so they smushed it in two distinct ways that made the ML model wrong, but the Bayes model okay because of the difference in what went here. And so, but I thought it was disingenuous the way they phrased their results as being better in Bayes, like, cause it was like they were trying to sell the new version of M+, as opposed to explain that estimator and model were conflicted.
Well, that is a huge conflict of interest, but.
Well, yeah, I mean, these people write papers to get you to buy the software. They're not the only ones that do that, by the way.
No, I know that.
There's plenty of people that are hawking their own software and they show that it gives better results in simulations.
So what do you think? Questions? Interested in seeing how we do this in JAGs?
Yeah.
All right, well, let's take a break. 10 minutes? Are you?
I'm done.
Is it good? Oh, you're done.
I'm done.
She's done. Thank you, Lisa.
I'm done.
Actually, I'll probably need you to help me go through the example because I will not do it justice.
Okay.
I can kill the stream. 10 minutes and come back and we'll start doing some more here. Can you send me that paper?
Yeah. Can you send me an email?
Yes.
Lisa-Hoffman.